So this is section 8.2, and this is going to be on graphs of other trig functions. So in section 8.1, we did the graphs of the sine and cosine because those were very similar types of functions. These other functions are all similar in that they have these vertical asymptotes to them. So if I start off just like I did with the sine and the cosine by just plotting a whole bunch of points, so I just picked, a whole bunch of points. Kind of looks random, but I also did this just to give us one full period of the tangent function. So negative pi over 2, the tangent of that is undefined. Now, that's because we know that the tangent is y over x, and at this point we have an x value of 0, so if you look at the unit circle, it's undefined because of that division by 0. Graphically, that means that we're going to have a vertical asymptote at that value. At negative pi over 4, so that's a 45-degree reference angle, we know that the tangent of 45 degrees is 1. That negative puts it in quadrant 4 where the tangent function is negative, so we get a value of negative 1. At 0, the tangent is 0. At pi over 4, the tangent's 1. And at pi over 2, again, the tangent function is undefined. So that makes up one period of the tangent function. So we get this asymptote at negative pi over 2, this asymptote at pi over 2. Then we have this point right here, that x-intercept, which also has a y-intercept there. Then we have this negative pi over 4 and pi over 4 business. The tangent function kind of looks a lot like y equals x cubed. Kind of looks like a cubic function. So it does follow, but never touches those vertical asymptotes. And just like the sine and the cosine functions, those do continue on forever, so does this. So the next vertical asymptote would be out here at 3 pi over 2, so we get another one of these little snaky deals, and they just kind of keep going both directions. So some things to notice about the tangent function. The range, remember the range is how far up and down the graph goes. So it goes infinitely up, infinitely down. The domain is trickier. It does go infinitely to the left and infinitely to the right. However, there are gaps along the way. So we say that the domain is all real numbers. And I don't know if you guys have seen this symbol before, but that's a symbol for all real numbers. So we say the domain is all real numbers except those vertical asymptote locations. So that would be odd multiples of pi over 2. So those odd multiples of pi over 2 would be like negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on. Now, those vertical asymptotes are excluded from the domain, right? The vertical asymptotes, as we talked about here with the domain, are at odd multiples of pi over 2. Now, why is it odd multiples of pi over 2 and not just multiples? Why do we need the word odd here? Well, one of the multiples of pi over 2 would be like 1, 2, 3, 4, 5. That would be all the multiples. And we know that it's something like, say, 2 pi over 2, which is just pi, that there's not an asymptote there. It's just at the odd pi over 2's. So it's the 1, 3, 5, 7, negative 1, negative 3. Those pi over 2 multiples are where those vertical asymptotes are located. Okay. The period, unlike the sine and the cosine, the period for the tangent is 180 degrees, or pi. It is an odd function, and that means it's symmetric about the origin. So you can kind of see that we've got this kind of mirror image thing going on across the origin here. The zeros, or the x-intercepts, are halfway between the vertical asymptotes. So those zeros occur at integer multiples of pi. So we have negative 2 pi, negative 1 pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. So integer multiples is another way of saying just like multiples of pi, as opposed to, like the odd multiples of pi over 2. So another way of writing integer multiples, if you want to be, you know, like kind of super sexy about it, you can just write that it's k times pi, where k is an element of the set of integers. So the set, just like the real numbers uses that kind of double-legged r there, the integers uses like a double-legged kind of the z. Why? I don't know. I'm sure it's like French or something like that, but now I kind of want to pause the video and go figure it out. Anyway, all right, yeah, I did just pause it and go do some quick Googling here. It's from a German word. It looks like the German word is Zahlen, which means numbers. All right, so we all learning something together. But anyway, so if you happen to see that written somewhere, you know, now you can translate and know what that means. All right, the cotangent. The cotangent looks just like the tangent graph. It's just flipped. So instead of a little snaky deal going in that direction, it's going this direction. And you'll notice that the intercepts for the cotangent are exactly where the asymptotes were for the tangent. All right, so the range is the same. The domain is all real numbers except the integer multiples of pi. The vertical asymptotes are the integer multiples of pi. That's 1, 2, 3, 4, 5. The zeros are at the odd multiples of pi over 2. The period is still pi. Now, check it out. These two are exactly opposite of what the tangent function was because the tangent and the cotangent are reciprocal functions. So if you think about it, these asymptotes came about because we took the whole, remember tangent was y over x. So if we had something like, say, 1 over 0, and it was undefined, and you flip that over, you know, you take that reciprocal, now you're going to get 0 over 1, which is 0. So sort of, we can think of this as the reciprocal of undefined is 0, see, like right here, and the reciprocal of 0 is undefined. So that's why these points that were our vertical asymptotes for the tangent function become the zeros for the cotangent, and vice versa. The cosecant and the secant functions, those are super crazy looking. Okay? They kind of have these like little humps like this. Now what happens here is that this is, remember, the reciprocal of the sine function. So what I did was I took this, you know, this kind of a pencil here, and I just did like a little dotted line that is the sine graph. All right, so the sine graph, you know, one period looks like that. Now, let's talk about what the reciprocal of these looks like. So I don't know. Let's just pick a random point. How about we pick a point right there? That y value right there, that y value is 1/2. All right. What is the reciprocal of 1/2? Well, the reciprocal of 1/2 is 2. Not drawn to scale, by the way. But so look, as we get closer to 0 here, these fractions are getting smaller and smaller. You know, think like, you know, 1/8, 1/10, 1 over, you know, 1,000. Like all these y values are getting super, super, super small. But when you take their reciprocal, they're getting super, super, super big. Same thing over here. Super, super, super small. Reciprocal, super big. Right here, you'll notice that there's a shared point between the two graphs. That's because here we get 1. The reciprocal of 1 is 1. Same thing down here. That you get, you know, the reciprocal of this little dotted line hump. You just kind of flip it over, there you go. The cosecant graph has vertical asymptotes to it that my sine and cosine graphs didn't have. That's because, just like we said last time, this is a 0 of the sine function. And those reciprocal of 0 is undefined. So anywhere the sine function was 0, all of its x-intercepts, that reciprocal is going to give you those vertical asymptotes. The period, just like the sine function, is 2 pi. So this is actually one period. So one period is made up of these two pieces. Unlike the tangent function that repeats the same thing. All right, this one, it's not just one period is that. One period is both of those humps. The domain is all real numbers except where we have those vertical asymptotes. And those occur at 0, pi, 2 pi, 3 pi, so we get those integer multiples of pi. There are no x-intercepts for this graph. And the range is a little bit weird on this. So if you just look at this red graph, the range seems to be everything from 1 up and everything from -1 down. There's nothing for the cosecant graph, that is. There's nothing in between -1 to 1. So that -1 to 1 region is empty as far as the graph goes. So my range ends up being two pieces. Remember, if you have two different intervals, you just connect them with using that little union symbol. I'm going to graph the secant function in the same way. So I graphed the cosine function with these little pencil dotted lines. And then just like for the last one, this little hump right here, its reciprocal becomes that hump. This little piece right here, its reciprocal turns into that hump. And all of these zeros for the cosine function, when you take their reciprocal, become these vertical asymptotes. Just like the cosecant function, it has a period of 2 pi. The domain is all real numbers except for where there's vertical asymptotes, and those occur at those odd multiples of pi over 2. Much like the cosecant function, it has no zeros, so it has no x-intercepts, and its range is the same as for the cosecant function. Now, you don't have to memorize these graphs. These are on the formula sheet that I gave you. Turn off that light so it's not, don't have that wicked glare there. So you can see, you get the one period of sine, one period of cosine, one period of the tangent, one period of the cosecant. This one was the best one that I could find to put on here. I'm not a super big fan of how it broke up the one period of the secant function. I think that's kind of ugly. And then there's the one of the cotangent. I mean, if this were, me, for that secant function, I would have chosen to, like go ahead over here and then just continue that little piece right there. And then have this asymptote right there at 3 pi over 2, if that were me. And then just not put that piece. I would just move this over here. That way I get that one period as just, two complete little humps there and not like, half of a hump, a full hump, half of a hump. No, that's just me. Okay, so graphing these is going to be very different than how we did the sines and the cosines. Okay, so let's just do one of these and see how it goes. So let's graph one period of tangent of x over 2. Now here's what we're going to have to do. You'll notice on your formula sheet that I gave you the vertical asymptotes for one period for each of those functions. So what we're going to do is take the argument, this thing right here, we're going to take that argument of that tangent function and we're going to set it equal to the original vertical asymptotes for the tangent. So the tangent originally had asymptotes at negative pi over 2 and pi over 2. So we'll set that equal to pi over 2, and we're going to solve that. And then we're going to take that equal to pi over 2. So there's my two original vertical asymptotes. Okay. So these are two separate equations. I'm going to solve them for x. Because this is division by x, we're going to solve that by multiplying both sides by 2. So that 2 goes away, that 2 goes away, and I get x equals negative pi. Coming over here, I'm going to do the same thing for this equation. Those 2's cancel, those 2 cancel. I get x equals pi. All right, so what does this do? What does this do? Get this. This tells you where your new and improved vertical asymptotes are. These are your new asymptotes. Everything else about the graph is going to pretty much fall in place if you have the asymptotes. Okay? So we get negative pi back here, and then we have positive pi. So you can tell that the graph is being stretched out because it was negative pi over 2 and pi over 2. So now the graph's being stretched out. Halfway between the asymptotes is the intercept. Is that x-intercept? And it's a tangent graph, so it's going to, kind of have this little snaky shape to it. This halfway point right here and this halfway point right here are going to be your 1 and negative 1 values. And those are going to be, for this one, pi over 2 and negative pi over 2. I'm not quite as strict about those. The only thing these are really going to tell you is how flat or how steep this graph is. So for instance, because this has a 1 right here in this kind of amplitude-ish kind of position, if this were a 2, then that would be a 2, that would be a negative 2. If this were a 3, that would be a 3, that would be a negative 3. So that coefficient there before the tangent function is going to tell you kind of how flat or how steep it's going to be. All right, so I did draw this out a lot prettier, a lot more color-coded here. So you take those original vertical asymptotes for the tangent function and you set that argument equal to those. You solve those two equations. That gives you the brand new vertical asymptotes. And then of course you can play the halfway game to get the 0. You don't have to do the stuff that we did with the sine and the cosine, where we did the whole, 2 pi over b to get the new period. If you wanted to, the original period was pi, and that coefficient of x is 1/2, so you do get a stretched out period. So, if you wanted to do that. Let's see, so that was negative pi over 2. It was at 1. And then that's pi over 2. Oops, sorry, that's negative 1. So yeah, there's how we're going to do all of these types of graphs that have asymptotes. The easiest way of doing all these without having to take into account phase shifts and period changes and all that other nonsense. This is so much easier than having to do all that. With this, all you have to do is take that argument and set it equal to the original asymptotes. Doesn't matter what function this is. All right, if it's one of these 4, you have 1 period of asymptotes right there. So you just set that argument equaling to those asymptotes, and then you solve it. That'll give you your new asymptotes, and then everything else just falls into place afterwards, because you know that halfway between those asymptotes is where that 0 is going to be. And then halfway there is going to be, your 1, negative 1, or if that coefficient is different, then. All right, so that finishes up the in-class portion of this section.